Hi friends, welcome back to the first session of the RayTracer Challenge in 2022 and welcome back to this series. I finally found the time to record another one of those episodes here and have some interesting development fun with you together in this new year. And as you have seen in the intro I have created, there is something special I wanted to show you in this new year, something I've created during the Christmas holidays where I had some fun playing around with different technologies. And two of those are actually JavaScript, or better said TypeScript, and Webassembly, and another one Webworkers. And I've created something that you can, once this video is out, use and play around with, the RayTracer REPL, which is available at raytracer.xyz. And it's essentially a web application that is the exact ray tracer we have created here during the last couple of months, compiled into WebAssembly, and I've created this web shell around it so that we can easily use it and edit the new YAML syntax, which I've introduced in one of the last sessions, and it is live rendered in the browser. And as you can see, if I'm clicking here on raytrace scene, it is lively ray traced in the browser. It is executing a parallel WebAssembly version of our ray tracer. It is parallelized as well using Webworkers. So in my case, I think about 8 threads I used. It automatically uses the amount of CPUs that you have in your system. And as you can see, I could, for example, change the light. I could, for example, do something like, okay, let's make the light a little bit bluish here, and now we have bluish light here, which now is live rendered in this browser. Or I could, let's make this light white again. I could, for example, have the plane move up a little. So let's check this one. Here are our y coordinate. Let's just move it up by, why not 2? It should cut then. Oh no, this was the this was the color, not the position. Oh, I don't have a position here, so let me quickly add this one here. So I'm adding a transform here, transform, and yeah, let's do a type is translate, and we want to translate this one to like 0 on the X, 2 on the Y, and 1 or 0 on the Z. And this should actually now render. It does not. Okay, maybe I used tabs here instead of, let's see. So, okay, now we have moved it too far up, so let's move it a little bit down again. And now, as you can see, it is cutting our spheres in half, maybe only a little bit. So I've just changed the code here, and as you have seen, the rendering is updating alive. And we are actually rendering 1280 pixels by 780 here by default. But I could, of course, change this to be full HD, like 180 by, 1920 by 180. And now it is rendering a full HD image. And I've set my zoom mode here to fit, so it is automatically zooming out there to make it fit into this canvas, which I can resize, of course. I can select different cameras. If I have a second camera defined here, which you will see here, I can select the camera here and I will see the different perspective, which is defined below here, or the main camera again. I can, of course, export the PNG of this render and save it. We have this auto render here, which causes the system, as you have seen, to automatically render once we change anything and try to render it. We can actually disable this, and now I can freely change things here around, and nothing will happen until I click this Ray Trace Scene button. That's for short what this system here allows me to do. Let me quickly show you how fast this is by quickly rendering a 4K image. Let's do this by 3840, and we have 21600. So this is now a 4K rendering in the browser live, and let's see how fast this is. And it is, I think it is astonishingly fast. So this is now a real 4K image. You can see if I remove the zoom, this is the real size of this image actually that I've just rendered within the browser, compiled our ray tracer to WebAssembly and build this shell around it. If you are opening this up for the first time, you will see actually this welcome tutorial, which will quickly show you the most important parts of the editor, which I've just explained to you, so you can get hacking. And the best of all, it's completely running locally in your browser, so there is nothing talking to the server yet. I'm thinking about maybe extending this one in the future with something like maybe a system to have it be able to load different YAML files from all the different chapters we are doing here, or even allowing it to save your own YAML files there, which you can then share with others or share with me and show me what you are doing and playing around with this thing. So that's for the future. For now, I'm very happy that I have built this thing. And in this session, I will go through the different steps I took to create this one, concentrating on the Rust side, on the Webassembly and Webworker side, of course, which is then talking to the WebAssembly and all that stuff, and not particularly on the UI and JavaScript side. If you would be interested in something like this, in a video which is talking about more like JavaScript and TypeScript development of such interfaces and stuff, just leave me a comment and maybe I will do one of those in the future then. Of course, the source code of this thing is available on my GitHub. The whole source code, which you will see now, is available on GitHub, and you can get it there and browse it and take a look at it. And yeah, if you want something added, don't hesitate to create a pull request for it, and I will happily consider it for integration and take a look at it. So yeah, let's take a look at this. And if you want to play around with it, it's, as I've said, raytracer.xyz. I liked it that there is such a domain free still. So yeah, I registered it for this. So okay, let's take a look what we are actually doing here. First of all, I guess I could yeah, maybe show you what I've done here. Actually, I've not integrated, as I've done the last time I played around with WebAssembly, this directly into the raytracer source code, but created a small wrapper library around it, which I then can transform and compile into WebAssembly and use, which uses the raytracer as a library itself, so that we can always build those things independent of each other. I can now change the raytracer and extend it, and as I've done before, and can then build this part here, this wrapper, using this raytracer library. So let's first of all take a look at the TOML file, I guess. So this is actually called the raytracer challenge WASM because it's a WebAssembly target. It's not that I specify the target here, it's only for me that I know that this package is the WebAssembly part. So yeah, we have a not really good chosen version here, but we don't care about that at the moment. We have some, go away. We have some things here that we already used in our first WebAssembly experiment, which you will find on my channel as well, if you want to take a look at this. Which is, for example, that we have this console error panic hook. So the moment that our Rust code panics, which shouldn't happen in our case, but the moment it panics, it will actually print this in the JavaScript console that we get the error. We have furthermore WASM bindgen here for tests as well as for the compilation itself, because we need a lot of different macros there from it, which allow us to ease the WebAssembly compiling and binding process, which we will see in a second. Then the most important dependency of all, I'm importing my main branch of the raytracer challenge in Rust repository here. So our work, which we are doing all the time when we are implementing this raytracer, as a dependency, so that I can actually access it and Cargo will check it out and build it for us. Then we are including this console error panic hook, not only defining it before. We are using valloc, which is a very small, it's a very small allocator, which allows us to have a very fast allocation. I'm not 100% sure why this comment is still in here, because it works and it compiles. Not 100% sure, maybe it doesn't even work and I'm just having this in there. I need to check this. Otherwise, maybe this comment is just old. I've copied this out from our experiments before. Then we are using JSys, which is essentially the part of a Rust library which allows us to access all the different JavaScript related parts. Like we have those specific JavaScript data structures that we can create. Like for example, in our case, we are creating pixel data for a canvas to be rendered in, and we have this image data structure there, which we can then fill with live and transfer it over to our JavaScript world. As you can see here, I'm only using specifically this image data part because I don't need anything else, and I want to make the WebAssembly target as small as possible in the end. Then I'm actually telling the system to not use wasm-opt, which is a call which is automatically usually done after creating a release package. But as I'm working here on an Apple Mac with an M1 processor, and there isn't a working release of wasm-opt for the M1, which is ready to be used. So there is no binary package there yet, which can be used actually. I'm disabling it here, and as you will see in a second, I'm then manually using wasm-opt, which I've just installed besides and compiled it myself. So this works quite well. And then I'm telling the system that if I'm creating a release build, I want to create a link time or I want to have link time optimization, which essentially with this fat configuration does is it links everything together, every module, and then it's doing an optimization cycle again. So it's essentially making things a little bit faster and a lot smaller actually, because it can throw out stuff that it does not need between the different modules it is using there. Usually I'm not using this because it's not worth the performance gain and not worth the size gain, but it takes a lot longer to do this while linking. But as we are creating something that will be downloaded with your client from the web, I want it to be as fast and as small as possible once I'm building a release version. Yeah, so that is actually everything that we are doing here. So let's take a quick look. It's everything that is Rust and therefore WebAssembly related is here stored under the Rust folder in our project. And we actually only have one librs file in here, which is not that big actually. So oh, I see. I can clean up here a little now. I've not opened up this file for quite some time. So yeah, maybe let's quickly do this, and then I can tell you what I'm actually doing there. So we don't need this anymore. Maybe we don't even need this. Actually, I guess we really don't need this. We will see in a second because I will be compiling this. So let me quickly comment this one out here. We don't use this anymore. So let me comment this one out as well. It was only debug code I had in there. So to be able to actually lock something into the JavaScript console while executing my, my code here. So yeah, let's see what we have here. As you can see, I have only 159 lines of YAML code there for what I need to do, because I really only wrapped those parts of my ray tracer which are really needed by our ray tracer REPL in order to work with it. So we are only wrapping something like parsing the YAML, rendering this data and getting back image information from that, and something like extracting the camera information from it to be shown in the menu and stuff like that. But a lot more things we don't need to do. So we don't need to expose that at all. So yeah, we have some initialization here. For example, the usage of the V allocator, which makes things smaller and faster a little bit. We have two macro rules here, which are creating errors for us. We will see that in a second, so that we can actually throw a JavaScript error from our Rust code. And then we have the most important part, which is actually our starting point. And our starting point here does not do a lot of stuff. It's just marked with wasm bindgen start. And yeah, it's what is called actually once we initialized our WebAssembly module automatically, so to speak. And the only thing that we are doing here is we are registering this console error panic hook I've talked about before, which then will, if the system panics, show this within the JavaScript console. Then we have a struct here, which is a camera struct. And this camera struct will actually provide us with an ID, a width, and a height. So I've created this and made it inspectable using this wasm bindgen macro, which allows us to access those values then later on in JavaScript directly, or convert them to JSON, for example, once we have filled and transferred them over to the JavaScript context. And this getter with clone is actually needed for the string properties, so that we don't leave this string within the WebAssembly memory block that is used for the WebAssembly execution of our Rust code. But we want to transfer it over actually into the JavaScript context, so that we can use it there, and it's not gone once we deallocated this object here once we had it. Yeah, then we are implementing the constructor of this camera object, which we simply tell to, yeah, you exist and you can be called from JavaScript as well. I'm not even 100% sure that I'm using this, but I implemented it nevertheless, or exposed it, better said, because I needed to implement it anyhow in order to use it from our Rust code. So it's just like any other construction function we have created before, to create code here, to create our object here. And then we have another object, which is the world object. And as you can now see, we have this pubstruct world here, and it uses internally the world object from our ray tracer. So I'm now referencing the ray tracer challenge world here as a world object there, just to be used within this object. And we can later on, we are binding this with bindgen, so we can access the data from in here later on from our JavaScript part. We have furthermore a hash map of cameras here, which have a string identifier, which is their name, and a camera object, again from our ray tracer challenge library. or our ray tracer. And now I have the implementation here, and the implementation is essentially what wraps all of the needed parts of our ray tracer in a way that we can use it from our JavaScript side. So we can construct a world which in turn takes a YAML string, or which takes a YAML string, which is then put into the world loader, which we've implemented in our ray tracer, and is then actually loaded. And in case this loader throws an error here, using anyhow, we are using our macro to translate this into a form which the WASM bindgen understands and will then give up to the JavaScript stack, so that we can work with this. So essentially it will then throw an error within JavaScript. We have just this encapsulation to make it a little bit nicer. And as you can see, that is essentially, you might have seen this before while I was typing here. If I'm, for example, let me specify a type here. Let's call not a sphere, but what do I know? I specify a pyramid here now, which we actually don't have. And I now click Ray Trace Scene. We will get the warning, unknown body type, pyramid, found at document 0, item 4, body. So it's essentially specifying that there is something wrong with this. And this error actually is directly coming from our Rust code. From the Rust code we have built into WebAssembly, and as you can see, once the rendering finished again and everything is fine, the error is going away there. But this error message is directly coming from this one. We are trying to load this world here in our WebAssembly, it is failing, and the error is transferred up into our JavaScript context. On the other hand, if everything is all right, we just return a new struct of our world class here, of our internal world class, which we've created here. And we have some certain functions here on our world, which is, for one, the getCameras function, which we are, because JavaScript uses a bit of another syntax usually for their method names. In Rust, we are using snake case. Or no, it's not snake case. How is this actually called? The one with the underscore, not the dash. We are using usually underscores to separate the different parts of our method or function names. In JavaScript, we usually use camel case, starting with a lowercase letter first for method names or for function names. And therefore, because I like it better this way, I'm just telling the WASM bindgen to export this getCameras function here as getCameras in snake case to JavaScript. And then, as you can see, all of those functions return either a JavaScript value, in this case it's an array, or a JS value. And so this actually is the result in case everything worked out, and this is the error value which is returned, which of course needs to be something that can be transferred over to the JavaScript side as well. And essentially this JS value here is what is created, for example, by those macros. If there is an error, they will return the error variant of this result here. With this JS value inside. So this getCameras thing doesn't something really spectacular. It essentially only goes ahead and takes from the camera objects, which our ray tracer parsed and created from our YAML file, an iterator walks through them and creates essentially a JavaScript array from them. So a JS array, so that we can return this one because we want to put it into the JavaScript context. Everything that we are giving to the JavaScript world needs to be encapsulated into a JavaScript type, of course, because we can't put a Rust data type in there. Most of the types are automatically converted or can automatically convert it into the corresponding JS types, because JSs has all the needed implementations for that. But an array is a little bit more complex because there might be, as you can see, there might be references of strings in there and stuff like that. So we have to walk through this and create the corresponding JS values from all of this and then push them into the array, and then we can return the array there. Yeah, and there is one more function in this, which is, yeah, a little bit larger, I see, but it's the render function itself, so the main part of which does the work. Actually, the render function is defined in such a way that we can provide it with a camera ID, which is one of the names of the cameras, which we can retrieve first here. And then we are providing the bounding boxes, or the bounding, the edge points, more to say. So a bounding box within our image, which we want to be ray traced. This is essentially more or less the same thing that we are doing within our usual implementation, which uses or parallelizes pixel by pixel. But as there is a certain overhead in calling such a render command here and dispatching it into the WebAssembly from the JavaScript, I determined it would be best to always render more than one pixel. So we are, I think, rendering 32 by 32 pixel blocks, or maybe even 64 by 64. I'm not 100% sure. We will take a look at this in a second. And what I can do here is I can specify arbitrarily sized pixels. So I'm specifying the top left corner here of the coordinate and the bottom right corner of the cutout I want from our ray traced scene. And what I'm then actually going is doing some sanity checks, like, for example, that there isn't provided an invalid camera ID or stuff like that. And once I have everything in place, I'm checking that nobody requested some part of the image which wouldn't be renderable because it's outside our canvas. And once we have checked all of those things and made sure that everything is all right and everything is within the given parameters, we are actually doing more or less the same thing with our rendering that we are doing always in our ray tracer rendering initialization. Yeah, we are iterating through our pixels, and then we are telling our world to ray trace and calculate the corresponding pixel for the canvas position we are putting in there. So this is the usual code as you have seen it before many times. And yeah, then I'm actually taking here the pixel index. So because we are returning the data as a flat array, so it's just a flat array of color byte sequences. Each byte, each color component of one pixel is stored as 1 byte. So we have RGB and alpha channel, as our ray tracer doesn't support an alpha channel yet. Maybe we will change that in the future, I don't know. But as it is the case, I'm always putting in full opacity here for the alpha channel, and the rest of it is actually, as it is encoded as a unsigned 8-bit integer here, or needs to be, I'm taking our floating point value, which we usually store, and map it to the correct range of values by simply multiplying it with 255 and then rounding the value should there be some precision that we need to take in away because we cannot properly provide it here. So that is essentially what I do. I create this data array, which we then use, and yeah, then you can actually see what we are returning here. We are, where is it? Render is returning a clemmed vector of unsigned integers. This clemmed is needed to tell the JSs that this is really always definitely a value between 0 and 255, and everything is all right with it. So we are just returning this data here. And this is then actually going to be transferred into the JavaScript world. So this is actually everything we need to attach our ray tracer, which we have built before in all of the other videos, to the JavaScript world via WebAssembly. We have a lot of glue code in the JavaScript world as well, which you will see in a second. Let me show you. This is actually the Rust part of it. So, oops, I didn't want to. What have I pressed there? Okay, I just wanted to check that my changes are actually still compiling. So let me do a quick npm run dev. npm is our node package manager, which I'm using as a kind of building running tool as well, because we need it anyways, because I have a lot of Node.js tools in there and a lot of Node.js and JavaScript dependencies, of course, for the front end. And as you can see here, the system is happily first compiling our JavaScript, our Rust into a WASM target, into a WebAssembly target. Then it is doing some more stuff, optimizing and so on. And then it's building our JavaScript part here as well. And if I now open this one up, maybe and hopefully in the browser 8080, it should still show us our, it still shows us our, let me quickly mark this one so this one will not come back. Yeah, it still works, so the code I commented out works as well. And as you can see, if I'm opening the debugger here and the network tab, you can see that it is actually loading, besides all the JavaScript stuff, it's actually loading this WASM file here, which is what we've now just compiled, and it's about 270 kilobytes. So our whole ray tracer is 270 kilobytes of Rust, of compiled WebAssembly. Our Rust ray tracer is 270 kilobytes of compiled and optimized WASM code, which actually is not a lot. I would have guessed that it will be a lot more, but it is not. It is quite concise and quite fast, and I really much like it. So where do we go from there? Yeah, you can see all the different requests there as well. Why it is requested so many times, we will see in a second as well. It's essentially because every of the web workers which we are spawning is getting its own copy from this one. It's not actually downloading it like 8 times or stuff like that. It's loading it once and then supplying it to all the different web workers, at least in a production build. It's requesting it only this many times in a development build, if you are wondering. So how we are now accessing this, we have created this WebAssembly file and we have now built it by, let's take a look at what we are calling here to build all this stuff. Once I'm calling this one, it will go into the Rust folder here. It will then call wasm-pack, which will automatically do everything the right way to compile our Rust project into a WASM file. And we are saying we want a release build here. We are targeting the web. We want a specific output name. And then wasm-pack will go ahead, compile our data, create a WASM file, and put it into the output folder. And once we have done that, as I've said, I'm using wasm-op directly because I've built it myself, and we are optimizing this output here and writing this to an output file here and taking this built WASM file. And once we have done this, we are replacing our optimized version with the one that was built before, and we are leaving the directory before, the Rust directory again. So you can see that it is really not that complicated to actually create a WebAssembly build, because the hard part is done by wasm-pack, wasm bindgen, and JSys. So everything else that is in here has to do with the web interface that is created itself. So we will take a look at this later on. So how is then this created system used? What it creates in the first place is For one, this WASM file here, which, yeah, I cannot open here because I've not a hex editor plugin in my code viewer, so why should I? But it's binary code, it's a WASM code. And it actually creates some more files. It creates this raytracer.xyz file, and it creates TypeScript definitions. The TypeScript definitions are actually quite nice because they are auto-generated, and as you can see, they reflect all the stuff that we defined and exported in our Rust files before. We have the camera class here in this case, because something like the Rust structs isn't available in JavaScript. They are classes, which has all those defined properties. It has the exported constructor. We have our world, which takes the YAML string here, and it has the getCameras function here, where the export is not 100% perfect because the system does not know that getCameras actually returns camera object, but as this is only the typing anyways and not the code that is run later on, this is not a real problem. And as you can see here, the render function takes in the camera string, the identifier, our bounding box, which should be rendered, and it returns an unsigned integer 8-bit clamped array, which is a JavaScript data structure which allows for quite fast and very low level storage and access of simple byte arrays, which we are using here to transport our rendered byte data, our color data. Then there is quite some other stuff. You might have noticed some of those free functions here or methods, and there is some more like this input-output WebAssembly stuff, which seems to encapsulate something like WebAssembly memory and some more internal functions. And those are actually automatically used by the created JavaScript file here, which we will take a look at in the second. This is created via WASM bindgen as well, and it does take care of all the not so nice parts of what needs to be done once you want to really use a WebAssembly environment, because once you are executing WebAssembly, a WebAssembly module needs a memory space where it can actually interact with objects and stuff like that, which will be automatically created and handled by our code here that is auto-generated. And it needs something like, it needs those functions, for example, to kind of create our ray tracer and our Rust structures there somewhere in this memory space, and then reference them into JavaScript, because those two parts need to talk to each other. And everything of this is done by this generated WASM bindgen generated code. And as you can see, it's actually not that much, and it doesn't get really a lot of much more if you have a lot more exports there, because most of the part is simply generic, like instantiating and creating then those internal heap stuff on this memory block that is assigned there, and freeing if there is an error or something like that, and stuff like this. And this can all be reused, so there isn't a lot in this which is specific to the things exposed. This, for example, is specific to the things exposed, but as you can see, it's not that much. So this is not really much code. It's just a very thin wrapper to make our life easier, to essentially allow then to have this JavaScript class, and to simply allow us to, where is the constructor of this one? Here. To simply construct this within JavaScript with make us a new camera class, and it will essentially take the needed data, allocate strings, transfer them over into the WASM memory, and then create internally this object within our WASM space. And we don't even need to see that specifically. We don't even need to know, essentially. So this is everything here auto-generated for us. And we are using it or I am using it here in a way which, no, this was the wrong directory. As you can see, here is a lot of stuff in here, like all the different components, like the menus and our render surface and split view. And I've created this with a framework, if you can call it like this, called Svelte. Maybe some of you know it. That's another thing I wanted to play around with Svelte. I've only created some very little project with it quite some time ago, and I wanted to use it to create something, and it was fun as well, and I've learned some things, and maybe I will do a video about this as well in the future. But we are not really going to take a look at those. Maybe a little bit, but not a lot. So where are we actually landing here? No, these are utility stuff I wrote. The main thing that is interesting here, that is actually talking to the web worker, to the WebAssembly, is via Webworker. Webworker are essentially the JavaScript and browser and web developer way of having multiple threads. And as we want to have multiple threads or processes or whatever, we want to parallelize things and be able to spawn it on multiple processor cores and stuff like that, we are actually using Webworkers. And Webworkers can be spawned in the background, and they are completely separated from the normal browser process and Java process which is running on the website. And they have then a communications channel, a quite limited but working communications channel, which allows us to then communicate messages between the main thread, the JavaScript loop, which is within the UI, and our web worker. And I have a render web worker here, which I've written, which actually then goes ahead and does all the heavy lifting for us, talking to the WebAssembly and giving us back something that we can really easily use. And I've encapsulated this so as a web worker so that I can spawn it multiple times. As you might have seen here when I'm rendering this, there are multiple of those squares appearing at once because it is rendering in multiple web workers simultaneously to speed things up, simply said. So this is actually encapsulating our rendering process. And I'm using a wrapper here, which is called comlink, to ease the communication with the web worker for me and stuff like this. But that's not that important. What I'm actually doing here is, where is it? I'm loading my WebAssembly file here. And this import statement is then actually processed by my bundler, which in this case is rollup, which bundles all of my JavaScript together and optimizes it and minimizes it and does a lot of stuff, which I've configured here, which has this WASM loader. And essentially this takes care of if it sees, did I close the file now? If it sees a file like this, a WASM import, it will make sure that it takes this file and let me show you, puts it into the right folder here. It names it according to, I guess, its checksum or stuff like that, so that if it changes, it's automatically reloaded and stuff like this. And it makes sure that it includes a short startup thingy that then initializes this WebAssembler module. It's only like 2 or 3 lines of code that essentially downloads it from the server once it's encountered, then initializes it, and then starts whatever is in this WebAssembly file. So it will automatically create this for us simply by importing it like any other JavaScript dependency. And as you can see, I'm importing those JavaScript parts of our interface here directly from our Rust package, which is created, which I've just shown you before. And so we can now using this. The init function is something special that is auto-generated as well. And yeah, so let's see what we have here. We have now our render worker, which will be exposed. Our render worker for once knows if it's initialized or not. It has a world it might hold. This is our exported world from our WebAssembly, from our Rust. It has our cameras map, so it essentially has this hash map of identifiers and cameras, which we have exported as well from our Rust world. And then it has this primary function here, which is initialized, which, yeah, simply if it's initialized already, we don't need to do anything there. And if it's not, we are actually going ahead and yeah, doing here something to load our ray tracer, which we get by, as I've said, this is what the loader then generates for us, the bundler. It will essentially be this, give us back this function here, which is an asynchronous function, which we can then call. And once we've called, we will get back the loaded and primarily initialized WebAssembly module. There isn't much to it. It's just like that. And we will get it back. And then we will put this WebAssembly module into the init function that our WASM bindgen on the Rust side, on the WASM bindgen side, created for us. And after we have done this, we are actually ready to use what WASM bindgen, like our camera and our world and stuff like that, created for us, and it will automatically know where the WASM context is and how it needs to be accessed and how it can talk to it, and we can simply use it like any other JavaScript object there, which is really nice. So what I'm then doing is I'm simply initializing our camera as a new hash map, and then setting everything to initialized. And now I have a wrapper here about the load YAML, which allows us to load a YAML. Let's take a look at this in a second. I have a wrapper here written which gives us all the cameras back. This is essentially used in order to populate the camera menu, which you have here, so that I can display those, because this information needs, of course, to come from the parsed YAML, and the parsed YAML is parsed by the WebAssembly code. So yeah. And then I have an actual function which is more or less a pass-through to our render function, which we've seen before. It takes a camera ID as well. It takes our bounding box to be rendered here. And now it does not return a simple array of color bytes, but it returns something that's called image data. And image data actually is more or less, it has internally this color byte array. This is essentially why we have chosen to return it like this, so we don't need a lot of post-processing, because that would just cause more CPU cycles that we don't need. But it's a data type which is used by the HTML canvas object, which is essentially what we need to render into here to store pixel data. And it's a specific interface which needs to be created then, or can be created, which has this color data array and has a specific height and width of what kind of color data or how many color data is in there. So we decided to return this here. And what I'm then actually doing here is I'm calling into our activated world here and tell it to render with the given parameters, and I get back my color data array from my WASM code, from my Rust code there. And then I'm doing a little bit of more magic. As I've said, Webworkers are using or are independent from the browser thread itself. But so if I wanted to transfer this color data information, this image data, to the main thread, I could do this, but I would need to copy all of those data through their communications channel into a new kind of byte array on the target side, on the browser UI side, and then I could use that there. For a moment, I would have the data twice in memory while it is copied, which isn't that kind of a problem because it's not that big. But I need to essentially copy this data through the communications channel, and this is not very efficient, of course. But luckily for us, there is a way to and we can use this transfer of my communications library, which I'm using there, which allows us to transfer the access to a specific memory region from the web worker to the main thread and vice versa. So what I'm actually doing here is I'm transferring the access rights to this memory, which I am storing those data information in here to the main thread, which means actually that at the moment I've done this, I have lost in the web worker the access to this memory region because it can only be mapped to either one of both. But it is not a problem because once we have done this, we are finished with this data anyhow. So it is essentially only transferring some sort of pointer through this communications channel to where the memory is actually residing, and then the UI thread can access it. And we need to, as we are getting this representation here from within the WASM memory space, we need to do a little bit of extra work here, which then actually allows us to do this. So we are actually internally copying this into the web worker space and then transferring this to the UI main thread. But it's a lot faster this way than if we would have transferred it through the communications channel. So this is actually why there is this extra code here, which you've seen here. But in the end, what I'm doing is I'm taking the data from the render call, which is which is here in our Rust code. Where is it? Render, there. Yeah, I'm taking this byte array, which I've created here as a result of my ray tracing and returned here, and accessing it more or less directly here in my JavaScript world, which is quite fantastic that this is working. I really much like it, and I really enjoyed that when I did that. And when I found out that this works this way and it's working this well. So now that I have this worker, let's take a look how this is actually displayed in the end. So once I now have this worker here, I have, let me close this folder here again. I have a component, where is it? Render surface, I guess I called it. TypeScript, build a Svelte plugin, yeah. After they save to disk, restart the TS server. What way? Okay, let me quickly start this again. There's something crashed in the background, I guess. Okay, so extension has been modified on disk preload. What the hell is going on here? Okay, is it now working? The Rust analyzer is analyzing our Rust code, and okay. So now this seems to work. So I guess this is where I'm actually, no, it's not the render surface I wanted to open. I wanted to open up our render pool. Yeah, I've created an implementation here now, which actually allows us to easily use this bunch of workers that we will now have for each thread or process or whatever. There is actually something within the browser that is called hardware concurrency, and we can therefore ask the browser if it is supported. This is why there is this default I entered there of 4. We can actually ask it how many parallel hardware threads it supports. If the browser supports it, but any modern browser, so actually any browser, I guess, which supports WebAssembly and what I am doing there, will allow us to ask this question here. And we can use this to determine how big our pool of workers will be. So, and there is actually the answer to the question I had before, which is what kind of blocks we are rendering per worker. So every one of those little thingies you see appearing there is always 64 by 64 pixel. I could change this here I can easily change this here. Let's do it like, let's for example render 8 by 8, and you will see that it then takes a lot longer because there's a lot more overhead. I need to run the dev server then again, and then you will see that this is actually having a consequence to our implementation there. Let's see. It bundles, and as you can see, all of this JavaScript bundling and dependency resolvement and then minifying and so takes some time, and I guess it wasn't even minified. No, that was the wrong button I pressed there. So yeah, should have been in here. And as you can see now, the blocks are a lot smaller, but the rendering takes a lot longer because there is a certain amount of overhead for each of those calls and transfers of data and stuff. And yeah, 64. A size of 64 was quite kind of the sweet spot which I determined, and it's working actually quite nice. Yeah, there it is telling us that everything was now broken because in the meantime I changed it, and now as you can see it's rendering here again quite fast. So yeah. And this is actually 64 by 64 sized blocks. So so we are defining this here, and then we have yeah certain basic structures here which holds our worker threads and knows if it should do something. And then we are actually having the more or less the same methods that we have on our worker thread themselves, worker themselves on our web worker, which is load YAML, get cameras, render, but they are passed through. So if we, for example, have a load YAML, we are actually telling every of our worker threads to pass the YAML. This will, of course, be a little bit overhead because all of our threads will then parse the YAML file, or will need to pass the YAML file. Each of those things will parse it on their own. But the YAML parsing is really not the problem here with regards to CPU cycles. So that's not a problem. You can actually have something like shared memory between workers, and I could have somehow shared the WebAssembly thingy, the running WebAssembly between workers, but then I would have had problems with memory management there and stuff. So I decided to do it this way because it works, and it is not a real problem. Because let's be real, the rendering, the ray tracing is what takes up all the CPU cycles, not the parsing of the YAML, the initial one. Then we have actually here this get cameras. I can pass that through as well. So it will then make sure that the worker pool is initialized, and it will essentially, in this case, only take the first worker it finds here and give me the cameras of it, because they will be identical from every worker because all of those have passed the same YAML. So it will be identical. And in our rendering cycle here, we will actually go ahead and take a worker out, get the cameras, ensure that the correct camera exists and stuff like that, and then we will go ahead and render each of those blocks with always the next free worker. So what I'm going to do here is I'm simply taking all of those workers, and once one of them is finished, I will take the next block that needs rendering and give it the next block. And this will actually happen again and again and again until all blocks are rendered. And once those blocks are rendered, we have them ready to, or we have ready what we needed. And the data is actually then for each block. Once every block is finished, we will give back some sort of block definition, which tells the renderer then, which displays it on the screen where this block was, and the data itself, which was created by this thread, and it's passed out by callback. So that then, this is actually the part which I had opened before, that this render surface here can now go ahead and have update cameras, render, has a render function as well, of course. And it should actually, yeah, it tells the pool to, first of all, it needs to acquire the render pool, which can only happen once the rendering is finished, if there's still one running before, because then all the workers are working and don't have time to do anything else. But once it has it acquired, I'm going ahead here and loading the YAML into it. Yeah, then setting the correct size after I've selected the camera of our output surface of our canvas. And what I'm then doing is I'm actually rendering here. This is the call to the function you have seen before, pool render. I'm giving it the camera ID and I'm giving it then here. And this is the callback, which should be called once any of the blocks is ready for display. So we are getting the data of the block here, and we're getting the block information, which actually is containing the bounding box, which is rendered, and we are only interested in the top left part of it. So we are only extracting x1 and y1 here. And then we are telling our canvas, our browser element, within the browser to put this image data, and this is actually why we encapsulated it before in this image data structure, to put this image data on screen at coordinate x1 and y1. And this is when the drawing on the screen happens, which you see happening here while the rendering is happening. And as this is a lot faster than rendering in the background, there is no stuttering or no hanging or waiting or the UI not responding, because this is a very negligent, a very easy and not very slow operation. And it can easily be done, yeah, multiple times. And the browser will only update its rendering surface and everything is fine once a block is fully there. So, yeah, once all of this is done, the pool is released again so that the next rendering can take place, and we are logging some very minimal information here. If I've opened the console and reload the page, you will see that the acquiring of the render pool was nearly instant, and then the getting of the cameras took a little, because I've reloaded the whole page now. If I'm doing it again, it will be a lot faster. So as you can see now, this is only 4 milliseconds, because the first time it is happening, the renderer threads need to be initialized. So once they are initialized, they will just stay around and wait for further rendering calls. And but as you can see, we actually render this 1280 pixel by 720, so a 720p actually image. We are rendering this in what we are rendering it in, yeah, let's say about 600 milliseconds. So 600 milliseconds full rendering time from start to finish, ray tracing time. This is quite, I think this is quite amazing that this works in the browser. Yeah, and there's some more code here which handles the zooming, for example, so that I can make it smaller or bigger or whatever, or have it fit and therefore adapt to the space that I have here, and for export and camera and everything I need there, essentially. That is in there. And yeah, there is a lot of more JavaScript code here, but most of the important stuff which communicates with the renderer, I've now shown you, or not only most, but that is the part that communicates with our ray tracer, essentially. And yeah, that was an overview of how this works and how this WebAssembly part is created and used. And as you have seen, it's really easy. You can, even if you want to do it with your own project, you more or less can take the part of this Rust folder here, which is very, very small. You can actually use this as the basis for how to do it. I haven't yet, but I will create a README on how this works, how you can compile it, how you can update it and run it, and start the dev server and stuff like that as well, and put it into the repository before publishing it, so before this video is published. So once you are seeing this, there will be a README in this repository. As I've said, I will put this up on GitHub. It will be available. The full source code that you are seeing here will be available on GitHub, of course. And yeah, you can play around with it and have some fun with it. I'm not sure where I'm linking. Okay, here I'm actually linking to my primary Raytracer Challenge repository, but I will add a link here in this repository, and there will be a repository as well, which is already there, but it's not public yet. It will be public once the video is out on GitHub, containing this REPL here. So that you can use it as well. And if you only want to use it, play around with it, once you are looking or watching other videos regarding the Raytracer and want to play around with a feature that we just implemented, or want to change something on by yourself and play around with it, you can really just open this URL here, just open raytracer.xyz. It is already online. I've just opened it here, as you can see. And yeah, you will have access to this REPL. It will most likely be a quite recent version always. So once a new video is out, I should be really quickly be able to push a new version of what we have done in our Raytracer to the web here as well, so that we can play around with it. And I will even maybe use this during my usual development sessions to then play around with a new feature, new construct, new visual thing. Like if we are implementing another shape, for example, I hope to have it ready here very quickly, so that we can even use this within our session itself to then play around with this shape and see how it is going and doing. And yeah, we will see. I really much like this thing. I hope you have as much fun with playing around with this thing as I had building it, and still having fun playing around with. One of the things that it does not really support yet is touch-based devices like a tablet, for example, or a phone. Essentially all the WebAssembly part and the rendering part and stuff like that works fine. That is not the problem. But a lot of the different UI components do not yet work out nicely with a mobile touch interface. I need to put some work into this, but I wanted to get this out of the door now. Yeah, and I guess I will do this in the future, and maybe then you can even use this thing on your phone, which is stupidly fast actually on my iPhone. I've tried it, and it's quite amazing how fast this thing renders there. But okay, yeah, I hope you had fun while I was presenting this first session in 2020. I know it was a little bit different than the other sessions, because I did not really implement something live, but I only showed you what I did before, but I couldn't have recorded or published all of this. I just wanted to do it in some quiet time during the holidays and have fun with it and play around with some concepts. And yeah, I hope that this is okay with you, and that you had still fun watching me explain how this is working and interacting. And maybe you have even learned something and can now play around with it and get something like this out of the door yourself. So visit the site, play around with it, give me a comment on how you like it, what you want there in the future, if there's something missing, if you have any problems, or even only that you like something especially, or that you think this is cool stuff, or drop me a line. I'm always happy if I have some feedback on my videos. And yeah, if you want to be informed once the next one of my videos comes out, please subscribe and hit the bell. And as always, if you liked it, please give me a thumbs up, because that really helps me with the YouTube algorithm, and that even more people then can find out about what I did there, and even more people have fun looking at this and looking at the videos and looking at the code and yeah, playing around with it. So I hope that I can go back to a more or less weekly schedule now with my ray tracer development from now on, and that I see you in the next video. So thanks and bye!